If you're a calculus student confused about limits or derivatives, you're not alone. Limits are usually skimmed through in the course, like something we have to get through before learning derivatives. And the limit definition of the derivative formula is mostly taught as some complicated formula to memorize. So naturally, students struggle with this topic. Limits are actually foundational to the concept of calculus as a whole, and the first rigorous definition of the derivative was based on the limit. Understanding this concept visually not only makes this topic easier to understand, but the graphical representation of the instantaneous slope visually illustrates the concept of the derivative, building a solid foundation for calculus. By the end of this video, we will derive all of the major derivative rules using this limit method, including the power rule, product rule, quotient rule, and chain rule. In this process, you'll also get a lot of practice evaluating complicated limit expressions and obtaining derivatives. We'll also find the derivative of ln, e, sine, cosine, and tangent using this method, though we will need a graphing calculator to finish the problem. This will set you up with a solid foundation to begin your calculus course. Now, first, let's start with some background information to make sure that you know everything that you should coming into this. The limit as x approaches some critical value, we'll call it c, the limit of f of x as x approaches that value. For now, let's just give it a capital L for limit. And what this means is, this means as x approaches c, what does f of x approach? And so if f of x continuous, then the value of L, if we evaluate the limit, that will just equal f of c if we plug it in as the value of x. There are some times, though, that f of x may not be continuous, and then the limit could be different than the actual function value. And there's some discontinuous functions where, maybe it's undefined at x equals c, but then the limit still could exist. And so basically with the limit, we're mainly saying what's happening near x equals c may be a little more important than what's actually happening at x equals c. And so to evaluate a limit, first just try to substitute in and see if you get a real number, and then that would be your answer and you're done. But then if you get something like 0/0, then that doesn't mean the answer is 0. It just means there's a little bit more we have to do. All right, so I'm also going to go over a little bit of limit arithmetic. That way we just have all the tools that we need to face any problem. All right, so we already mentioned we'll just refer to the limit kind of in a shorthand with the capital L. But that basically means the limit of f of x as x approaches our c value. Now, there's also a couple of little tricks we can do if we have multiple limits or multiple things inside the limit. So the limit as x approaches c of a times b would equal the limit of x approaches c of a times the limit x approaches c of b. And this works for division as well. We also can have the property that the limit of x approaches c of e to the a, since e is a constant number that does not depend on x, then the limit does not apply to e, and we can actually transfer it to just the exponent. And similarly with e, we could have the same relationship with ln. So let's say if we had the limit of ln. Ln is just its own function, and so it would actually be equal to ln of the limit. All right, there's a couple more. So, for example, if we had the limit of, let's say we have some constant that's multiplied by our entire function. Again, if it doesn't depend on x, the big idea, if it doesn't depend on x, that we could actually not include it with the limit. And there will be times where all these will be useful for us. All right, and then the last one, so we have the limit. If, let's say, we had our whole function to the power of an exponent, then that would also equal the limit as x approaches c of our function. And then that whole thing, the exponent can transfer. So it doesn't matter in which order that you do the exponent or the limit, is basically what that one is saying. All right. So that's the basics about the limits, and we'll kind of refer back to these rules as we work through a couple of these problems. So now that we talked about that, we're gonna take a little step back and just review slope. Right. So as you probably know, right, we got like an x1, y1, x2, y2. The slope is going to be our change of y over change of x. Right, and I'm just reviewing that because that's really the basis of the limit definition of the derivative. And just to also connect this in a calculus way of thinking, if the slope is going to tell us the relationship between y and x. So how much is y changing based on how much is x changing? And calculus is all about rates of change and relative rates of change between variables and stuff. So this is really the foundational ideas of calculus. If the slope is positive, then that means that f is increasing, like the line that I drew here. If the slope is negative, if it was going down, then that would mean that f is decreasing. And if the slope is 0, that would mean it's a flat line. A straight line has a constant slope for all x values. But then, now we get into calculus and there's squiggly curves, different slopes at different x values. And so on a curve, the slope can change from point to point. So rather than having, this kind of discrete slope across a window of x values, in calculus, we want to know the exact slope at an exact point. And so our slope formula here is based on two values, two pairs of x and y. So how do we calculate a slope at a single point? And so this brings us really to the main lesson, is the limit definition of the derivative. That's what this is all about. So let's say we have some curve. Right, and I want to know what's the slope at this x value right here. And if I'm just guessing based on, visual, maybe it looks something like that. Right, and I'm talking about the slope exactly at this one point there. And so then what I want to do is, instead of, from x1 to x2, I really want to measure the slope from like x1 to x1, just only at x1. And so we can think about that by basically saying I want to add the very lowest possible number that I could possibly add, the number that is the very closest number to x. That way, I'm getting the closest to the true instantaneous slope at that exact location. And so we're going to just kind of represent this mathematically, still using the 2 points. But now we have this plus h. And so the h is the horizontal separation of our x values. We want to consider what would happen if h became almost nothing, so that it was x and the number very close next to it. And so we want to know, the limit as that horizontal distance reduces to zero, as that horizontal separation becomes infinitely small, as h approaches zero. And then, we just have our formula for the slope. So we've got our x values. This is our y value, right? X, the y value paired is f of x at x plus h. The y value paired with that would be if you plugged in x plus h into your function f of x plus h. And so really we're just basically saying we want to measure the slope as this horizontal separation between our paired points approaches nothing, right? And so that would be y2 minus y1. So it's f of x plus h minus f of x, and then divided by x2 minus x1. So that's x plus h minus x. All right. And this is the limit definition of the derivative. We're just going to clean it up a little bit because we've got an x and a minus x. So I really prefer to see it this way rather than just some complicated memorization, um, because it's really not, I guess, not too complicated. When you see, it's just the slope, and we're just basically saying the slope as we approach measuring only at the same point, as that horizontal separation goes to zero. All right, and so this is fine and all, but notice that we have a denominator of h, and we're trying to figure out what happens as h goes to zero. And so that should be a red flag right away, because we can't divide by zero. And so most of the time when we're doing these problems, especially on like polynomials and stuff, it should normally work out where the denominator will cancel away, so that we can obtain a real value. But then when we get into, maybe some of the more complex ones like sine, cosine, ln, the ones that are, real curves and stuff, that's where it gets a little tricky. But that's where we're just going to use a graphing calculator to kind of determine a couple of information that we might need. But anyways, let's go ahead and get into it. Example 1. We're going to use the limit of the derivative for all of these functions, and so I'll just write the function. Example 1 will be f of x equals x squared. Okay, so referring back to this formula, it just looks like we need to figure out, okay, what is f of x? What is f of x plus h? And then maybe we'll see if we can plug it in and see what happens. So that's f of x. What would be f of x plus h? All right, and just, a little refresher on functions. All that means is you just plug in x plus h literally as the value of your function. So since it's x squared, we replace the x with x plus h. Okay, and then it looks like we could probably do some work on that to expand it out. So it'd be doing the FOIL operation on that. So we get x squared plus xh plus xh plus h squared. Okay. At this point, it looks like we have what we need to at least just kind of attempt with here. So our instantaneous slope, the derivative of f of x equals x squared, we're going to try to determine it with the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. Okay, and then see what happens. Well, we got an x squared minus an x squared. And so then this will simplify. Limit h approaches 0, 2xh plus h squared over h. Okay, perfect. Now, one thing just, about basic arithmetic, if we have a plus, then every term has to have something if we're going to cancel or factor it out. And so in this case, right, we got an h here, we've got an h here, and an h to the power of 2. We reduce it to the power of 1. And look at that. Now that denominator has gone away. And so we'll be able to actually evaluate what happens at h approaches 0 now. So that would be 2x plus h. Okay, now what happens as h approaches 0 here? This thing, h, will just go to 0. So then this will just equal 2x. And so what this means is, right, remember, this is also the definition of the derivative. The derivative is a formula that measures the slope at any x value. And so what that means is that for the function x squared, the slope of it can be found by 2x at any x value. And so the way that we can write that is the derivative is the change over the change of x. This is just the lowercase delta, meaning change. The lowercase delta used because we're talking about change over a smaller distance. So the change as x changes of x squared equals 2x. All right, example 2. Let's do f of x equals x cubed. Okay, so just like last time, we're going to refer back to the formula that we derived for the limit definition of the derivative. We just need to figure out what's f of x, what's f of x plus h. So that one is going to be, instead of x cubed, we're going to have x plus h cubed. Okay. We did just figure out x plus h squared, right? And so it'll just be that times x plus h. And so let's just refer back to the work we already did. X squared plus 2xh plus h squared times x plus h again. All right. And so then What's that going to simplify to? All right. We're going to have x squared times x cubed, plus 2x squared h, plus x h squared. That's just the x multiplied by each thing, and then the h multiplied by each thing. Plus x squared h, plus 2x h squared, plus h cubed. Okay, well, there you go. We got our f of x. We got our f of x plus h. So now we want to figure out what is the limit as h approaches 0 of f of x plus h minus f of x over h. So x cubed plus 2x squared h plus x h squared plus x squared h plus 2x h squared plus h cubed minus, that's our f of x plus h, now minus the f of x cubed divided by h. Okay, let's see. Well, first of all, we got our x cubed minus our x cubed. And so now we're in the same situation as last time, where everything added has an h. So we can also just go ahead and cancel that in this step too. Right? So we're just going to reduce the power of h by 1 in each term. So that would be xh to the power of 1, x squared, that h goes away, h squared goes to the power of 1, h cubed goes to the power of 2. Okay, we rewrite it a little bit cleaned up. Limit as h approaches 0 of 2x squared plus xh plus x squared plus 2xh plus h squared. Oh wait, no denominator. Okay, now what happens as h approaches 0? Well, anything that is multiplied by an h is going to go to 0. And so then we can just evaluate that, right? That's 2x squared plus another x squared. So that'll be 3x squared. And so remember, this method is the definition of the derivative. And so our function was x cubed. And so what this means is we're saying that the derivative of x cubed equals 3x squared. Now, let's see if we can notice a pattern. What we're doing, by the way, is the same thing that the mathematicians did when they first discovered this rule. But okay, we have function and derivative. So let's make a little chart and understand what we're looking at. So function and the derivative of the function. All right. When it was x squared, it was 2x. When it was x cubed, it was 3x squared. What's the pattern that we see? So as we go from the function to its derivative, we multiply the exponent by the coefficient, and then we reduce the exponent by 1. So this 2 gets multiplied by the 1 and becomes the coefficient, and then it reduces by 1 to have the exponent of 1. The 3 multiplies by the 1 that was the coefficient there. And so that's why the coefficient becomes 3. And then it reduces by 1 to become a 2. And so this one is what we call the power rule. And basically it just says that the derivative of x to the n equals, what do we just say? We say multiply the exponent by the coefficient, so it would be n x, reduce the exponent by 1 to the n minus 1. All right, let's do example 3. We're going to do the same method using f of x equals x squared minus 2x. Okay, so that's our f of x. We also need to know our f of x plus h. All right, so f of x plus h, in this case, we're going to plug in x plus h as the value of x. That'd be x plus h squared minus 2 times x plus h. All right, then we're just going to clean this up. All right, x plus h squared, remember that's just x squared plus 2xh plus h squared minus, that minus 2 goes on both the x and the h. So minus 2x minus 2h. Okay. So then now the derivative of this is going to equal the limit as h approaches 0 of f of x plus h, x squared plus 2xh plus h squared minus 2x minus 2h minus f of x, x squared minus 2x. It's important to use a parentheses if you're substituting in the whole function there, because there is a minus sign, and that minus sign needs to go with both of those terms. Yeah, and then we have our denominator h. That's our formula. All right. So then what happens? Usually the same thing that we've been doing so far is this kind of x terms minus x squared minus 2x minus 2x. They end up canceling so that everything now is only in terms of h. And now we can get rid of that denominator by reducing every h exponent by 1. And now we can evaluate the limit, since now we're not going to be dividing by 0. So that's 2x plus h minus 2. All right, plug in h equals 0, and what happens? You get 2x minus 2. And so what that means, right, remember this is the derivative of the function. And so we're saying that the derivative of x squared minus 2x equals 2x minus 2. And so we already, established the power rule, right, as, You take the 2, multiply by 1, reduce it. So that'd be 2x for x squared, right? The x to the power of 1 would just be -2. And then x to the power of 0, it just becomes a 1. And so we notice that the power rule is valid for all polynomials, right? Like if it's separated by a plus or a minus. You just do the power rule on it one term at a time. Okay, example 4. Now let's do the same method using f of x equals 1 over x. All right. So what we've been doing before, we just want to figure out what's f of x, what's f of x plus h, and then put them in the formula. So f of x plus h, that would just be 1 over. Plug in that, so 1 over x plus h. All right, we're ready to go. The derivative of 1 over x equals f of x plus h minus f of x over h. And I should have said the limit of this as h approaches 0. And so what's going on here is we need to subtract these 2 fractions. And so in order to do that, they're going to need to have the same denominator. And so they don't have anything in common, so then we will just multiply them by each other's denominator. And we'll do it in a way that we're just multiplying by 1 so that we don't change the value of anything. But this way now both of the denominators will be x times x plus h. Right. So we're going to have the limit as h approaches 0 of, all right, and then this one will become x over x times x plus h. I guess we should go ahead and multiply that out. That would just be x squared plus xh. And then that's going to be minus, now we've got x plus h times 1 over x times x plus h. That's x squared plus xh. All right, and that's divided by h. Okay. Well, now that our 2 fractions have the same denominator, we can combine them into the same fraction. So that would be x minus x plus h over, wait, be careful with that parentheses there. X minus x, and then also minus h over x squared plus xh. That's our numerator divided by h. Okay. Well, if we look here in this numerator thing, we've got x minus x. And so then that just gives us negative h divided by x squared plus xh over h. And so now since we have the numerator of our numerator divided by this h, that will cancel, just become a -1. So the limit as h approaches 0 of -1 over x squared plus xh. All right. Now we got rid of that h in the denominator, and so we can evaluate this limit. So what happens when h equals 0? This term will just go away because of the h. So then that's just going to be negative 1 over x squared. And so what we found with this then is that the derivative of 1 over x is equal to negative 1 over x squared. And there is a more intuitive way of writing this, right? Because 1 over x is equal to x to the negative 1. So the derivative of x to the negative 1 equals, forget about what we wrote here. Do the power rule on that. Negative 1 times 1. Now reduce the exponent by 1. Same answer. And so the power rule also will work with a negative exponent. Example 5. Let's do the same method with 1 over the square root of x. Okay? Well, just like before, we need to find our f of x plus h. Okay? F of x plus h, that's just going to be 1 over, instead of square root of x, we got square root of x plus h. All right? So then our slope that we're looking for, the instantaneous slope, the derivative of f of x, that's going to equal the limit as h approaches 0 of, and we got f of x plus h, 1 over square root x plus h minus f of x, 1 over square root x, that's divided by h. Okay, so again, like the other ones, now we have this h in the denominator. We can't evaluate this limit because it would be dividing by 0. But what we can do, right, is since we have this subtraction operation, that's going to be the only approach we can take to move forward. And so we need to get a common denominator for these, just like we did on the last one. So square root of x plus h, square root of x, we're just going to multiply these by the other denominator, and we stack it so that it equals 1, so that we don't change the value of anything. But now we just kind of force the denominators to be the same. All right, so this derivative then is going to equal the limit h approaches 0. And so this first one is going to be 1 times the square root of x over the square root of x times the square root of x plus h. That because they're multiplied, they can go under the same squared. So x times x plus h together under the square root. And then same thing, we got 1 times square root of x plus h divided by square root x times x plus h. Okay, that is all divided by h. Okay, so now at least the next step we can do is, since our numerator subtraction operation has the same denominator, we can combine that as one fraction. So then that would be the square root of x minus the square root of x plus h divided by the square root of, and that would just, x times x plus h is x squared plus xh. All right, and then that still divided by h. All right, so that's our numerator there. Huh. All right. What should we do next? Well, this one now, there is a common trick that well, actually, before we do that, we can simplify this. Rather than having three fractions, we can combine the denominator of our numerator with the denominator. It'll make it a little easier for us. Okay, so then we'll just have square root of x minus square root of x plus h divided by h times the square root of x squared plus xh. Okay, yeah, that's easier to work with. Okay, now how do we move forward from here? Just as a background information, right? The square root of a plus the square root of b does not equal the square root of a plus b. And then same with subtraction. So do not try to combine that numerator. That will not work. But what we can do, a lot of times in algebra, if there's, like two numbers that you're subtracting or something, you don't know how to deal with them, what you can introduce is called the conjugate. And so, for example, the conjugate of square root x minus square root x plus h, and we're just going to take it and flip the sign of the other one. So square root of x plus square root of x plus h. And there's just advantages of basically multiplying by the conjugate, but like stacked on each other. And so that's what we'll do. So this turns into the limit h approaches 0 of, now we're going to have the square root of x minus the square root of x plus h over h times square root x squared plus xh. Now we want to bring in that conjugate, which is square root of x plus square root of x plus h, and we're going to multiply by it in such a way that we don't change the value, right? So the numerator and the denominator have to be the same, so that it's like we're multiplying by 1. Okay. Just be a little careful with your order of operations. All right. So it's just like FOIL on the numerator side, right? First times first is square root of x times square root of x. That's x. The outsides would be square root of x times square root of x plus h. So I'll just write square root of x squared plus xh. The inside would be minus square root of x plus h times square root of x. So then that'd be minus x squared plus xh. And then we've got minus x plus h squared. So minus the square root of x plus h squared. All right, the bottom side, this one is just one term multiplied. So it's not like FOIL, it's just a 2 distribution. So then on the first term, we're going to just multiply by square root of x. So we got h square root, and then everything in this denominator will just increase by the power of x. Maybe it's better to keep it separate, actually, now that I look at it. Yeah. So that one, instead of writing x squared plus xh, um, we're just going to substitute that with what we had before, x times x plus h. And actually, we can even just leave it separate, to be honest. The way that everything is going to cancel out, I think that's going to be the cleanest way to do it. All right. Because then, yeah, it's actually not so complicated to just multiply that. So then that just means the square root of x becomes x times h times the square root of x plus h. And then the other term, now we've got x plus h. So that'd be, it's a plus, h x plus h square root x. That one will cancel. This square root of x plus h squared, that's just x plus h. And so then we also have an x minus x. All right, and so then that's gone, that's gone, that's gone. We just have negative h in the numerator after all of that. Here we've got h times x times the square root of x plus h times x plus h times the square root of x. All right, h in every term. I think we're good to go ahead and evaluate this now. So now the limit as h approaches 0 of numerator becomes negative 1, x square root x plus h plus x plus h times square root of x. All right, what happens when h equals 0 there? Negative 1. The denominator then, we got x times the square root of x plus 0. And then we got x plus 0 times the square root of x. Those are actually the same. So then this turns into negative 1 over 2 x times the square root of x. All right. And so let's look at this one. This one was 1 over square root of x. So what this means is we're saying that the derivative of 1 over square root of x equals negative 1 over 2x times the square root of x. But what if we rewrote this as an exponent? Could we solve this with the power rule too? Because it's in the denominator, it's going to have a negative exponent. And because it's a square root, its exponent would be to the 1/2. So without looking at what we did the long way, can we do the power rule on this one too? So we take that negative 1/2 and we multiply it by the 1. And then we take that x. And then we reduce the power by 1. So negative 1/2 minus 1, that becomes you minus 2 over 2, that becomes minus 3/2. X times the square root of x is equal to x to the 1 times x to the 1/2, which is equal to x to the 3/2. So these are the same. So the power rule works. It works as well. All right, let's do example 6. Now let's do the same method for a more of a calculus type of problem using f of x equals e to the x. This one, we're going to need a graphing calculator for it once we get towards the end. So let's see. We're going to use our limit method. So we need f of x. We need f of x plus h. So what would f of x plus h be? That'd be e to the x plus h. All right. And so then we can find the derivative of e to the x as the limit of h approaching 0 of f of x plus h minus f of x divided by h. How are we going to do this one? Well, one thing that's important to remember is that if you have, say, e to the x plus h, that would be equivalent to e to the x times e to the h. And so this could be rewritten as e to the x times e to the h minus e to the x over h. All right, and then that allows us to factor out that e to the x, which is shared in both of the numerator terms. So we get e to the x times e to the h minus 1 over h. All right, and we discussed this towards the beginning, but remember, because e to the x does not depend on h, well then the limit doesn't depend on e to the x. They're just doing their own thing. And so this just becomes the limit as h approaches 0 of e to the h minus 1 over h. And then whatever we get for that, we just multiply it by e to the x. And so that makes the limit a little bit easier for us to obtain because now we just have one variable as opposed to two. And so this is where the graphing calculator is going to come in. So we're just going to graph e to the h minus 1 over h. We'll substitute in x because that's how the graphing calculator is going to work. And let me just paste that over. All right. And so we can just take the limit graphically sometimes when we don't really have a numerical way to do it. And so that's what we're going to do here. So we're looking at the curve of e to the x minus 1 over x, which is the same thing that we're trying to evaluate the limit as h approaches 0. So what does the function value appear to be approaching as x equals 0? Looking right here, right? And so what this tells us is that the limit as h approaches 0 of e to the h minus 1 over h as h approaches 0, then the value is approaching 1. And so we can just substitute that in for this whole thing, this whole limit expression. So then this whole thing, actually, the derivative of e to the x just becomes e to the x times 1. Did it change? No. The derivative of e to the x is itself, which is a super fascinating concept just on its own. But one way we can think about this is that e is the base used to describe natural growth rates like population decay, universal expansion, stuff like that. And so E is this kind of seemingly random number to us. It just never ends. For whatever reason, it has significance in our universe. And it is kind of considered the growth rate of the natural universe. And so it is quite fitting then that the derivative of e to the x, which explains, the growth rate, it is just itself. So it is its own growth rate. So that's a super important concept for calculus as well. All right, let's do example 7. What about ln of x, another important function for us? So just like last time, we just want to figure out what's f of x, what's f of x plus h, and see what happens when we take the limit as h approaches 0. So for f of x plus h, that'd be ln of x, substitute in x plus h, ln of x plus h. Okay? So then the derivative of ln of x is equal to the limit as h approaches 0 of ln x plus h minus ln x over h. Okay. One thing that you might remember, right, is that we have ln of a plus ln of b is equal to ln of a times b, and likewise with subtraction, ln of a minus ln of b would be equal to ln of a divided by b. There's lots of other important limit rules. We'll just stick to those for now. Because now, right, we have these two things subtracted. And so we can combine those two limits, ln of x plus h divided by x. And now that's divided by h. So now, what can we do? Well, the only step forward that I see is in that ln term. And so what can we do in there? The limit as h approaches 0 of ln of, well, we have that kind of fraction with two things. Maybe we can split the fraction into two and see what happens. So x plus h over x, right? That's equal to x over x plus h over x. And this x over x is just 1. So then we've got the limit as h approaches 0 of ln of 1 plus h over x over h. All right. And we're going to do a little weird trick here. But this just makes it possible to solve it. We're going to define a new variable. That way we can just arrange this in a better way, because that h over x is just really inconvenient. And so what we want to do is we want to replace that. Let's just call it u. So we're going to define this u variable as h over x. And so since our limit is in terms of h, then we also want to kind of translate the limit in terms of u instead, because we want to get rid of h. We don't want to worry about it. And so that means we also need to do something to that limit. And so how can we represent h? If we want to substitute it out, we can use this expression here from u equals h over x. H is equal to u times x. And then since x is not dependent on h, that means we can still substitute in u going to 0 without having to worry about anything like that. And so let's see what happens. So now we want to know what happens, as h goes to 0, our denominator of u will also go to 0. Right? So now we can talk about u instead of h. So as u goes to 0, ln of 1 plus u over u times x. Right? Because that's what h, we're substituting ux in for h. Right now, previously we had factored out an x term of the limit when it was h going to 0, right? Because we had said x terms don't depend on h. Now we have u going to 0. And x, x does seem to be related to u, right? We have formulas saying that. However, we can still pull it out, because the only reason that u is approaching 0 is because h is approaching 0. And so we're not like x is independent of all of that. So we can still factor out this 1 over x, right? Just to be super clear, I'll just write what that would look like. So with factoring out that 1 over x, then we would have ln of 1 plus u over u. And now that 1 over x is not really dependent on our h going to 0, right? Because the u going to 0, we replaced it just because h is going to 0. And so actually, that 1 over x is happening independently of all of that. So we can pull it out, and that simplifies the expression. And now, similar to last time, where we reach a point where there's really not any way to move forward numerically without, I mean, there is, but not with the current understanding, right? And so what we can do in place of that is we can just graph it. And so we wanted to know what was the limit as u goes to 0, ln 1 plus u over u? So I just graphed that with using x instead of u. So we want to know, what is the value of y as x approaches 0? And it looks like it's approaching 1. And so what that means then is it means that the limit as h approaches, oh wait, we're using u. The limit as u approaches 0 of ln 1 plus u over u, that's equal to 1. And so then we can just substitute that in there. And so this problem, we're looking for the derivative of ln of x. Right, and we said that's just 1 over x times 1. And so it's just 1 over x. All right, that's an important one. You just expected to memorize it. I mean, not the whole step, just the answer. All right. So example 8. Let's do the same method using sine of x. All right, so we're going to find the derivative of sine of x. What is f of x plus h? Sine of x plus h. Okay. So then we're ready to go ahead and try and figure it out. The derivative of sine of x, that would be equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, we're going to need to pull into some of these trigonometric identities. One trig identity that we have is that the sine of a plus b, that's equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. And the reason we do that is because this x plus h, we can separate out the h terms and the x terms from the sine. Right, and so our derivative is going to equal the limit as h approaches 0. Now, instead of sine x plus h, now we've got this expression here, where we're going to use a as x and b as h. And so then it would just be sine of x times cosine of h plus cosine of x times sine of h minus sine of x over h. Okay. Well, we cannot factor the sine x out of every term, right? We can take it out of here and here, but not the other one. But honestly, I think that's going to be the best way to move forward, at least just kind of factoring it out where we can. So if we factor out that sine of x, then that's going to be multiplied by cosine h minus 1. And then we still have this middle term, cosine x times sine h in our denominator. Now we have this really big fraction maybe the next best thing to do is just split it up. So that gives us sine of x times cosine of h minus 1 over h plus cosine x sine h also over h. And remember before we had talked about we can split these two limits. Anytime we have a plus or a minus, we can actually evaluate the limit of each term separately. And so that's going to be the best way to move forward here. Right, and so we're saying that the derivative is going to be equal to the limit of h approaching 0 of sine x times cosine h minus 1 over h plus, now this other term, we can calculate just the limit of that part independently of the other one. So cosine x sine h over h. Okay. Now, again, remember anything that is a constant in terms of h, if it doesn't depend on h, can be pulled out of the limit expression. So in this first term, we have a sine of x that has nothing to do with h. So that'll be sine x times the limit as h approaches 0, cosine h minus 1 over h plus. Now in the second term, we have the cosine x, which is not dependent on h. So we factor out that cosine x times the limit as h approaches 0 of sine h over h. All right. And so then, once we get to this point, there is a way when you learn more calculus, but at this point, we are gonna just use the graphing calculator to try to determine this limit. And so we can just graph both of these, right? Cosine x minus 1 over x, sine x over x. And we want to know what happens at h equals 0. Right, and since we use x for our graphing, it's when x equals 0. And so what this tells us then is that the limit as h approaches 0 of cosine h minus 1 over h, this first term, that's this green line, which has a value of 0. And then the other one, the limit as h approaches 0 of sine h over h, just looking at the graph, that one is equal to 1. And so then what we get is we're saying sine x times 0 plus cosine x times 1. And this expression we're solving for, remember, is the derivative of sine x. And so what we're saying is that the derivative of sine x equals cosine x. All right. Example 9. Let's do. Let's see if we can figure out the derivative of cosine x. So we got f of x is cosine x, f of x plus h, cosine x plus h. We're gonna generally follow the same strategy for sine and cosine. So let's see what happens. We got our f of x. We got our f of x plus h. Now we're ready to put our derivative formula. So the derivative of cosine of x, that's equal to the limit as h approaches 0, f of x plus h minus f of x divided by h. All right, so last time, remember, we had our sine a plus b relationship. We're going to look for the same one based on cosine, right? Cosine of a plus b is equal to cosine a times cosine b minus sine a times sine b. And so then that means this expression will turn into limit as h approaches 0. For the cosine of x plus h, now, right, we're going to use a equals x and b equals h. And so then that's going to give us cosine x times cosine h minus sine x times sine h. And then that's going to be minus cosine x divided by h. All right. So remember the general strategy that we took for this complicated limit before was we can at least factor out what we can and maybe get, at least like a clumping of 2 of these instead of, 3. And so we have this cosine x in 2 of our 3 terms. So we can factor it out from where we can. So let's see, that'll be cosine x times. Now when we factor it out, we're going to have cosine h minus 1. And remember last time we also just split it into 2 fractions. Let's just go ahead and do that here. All right, so then that takes care of the first and the third term. That middle term still remaining would be minus sine x sine h over h. Okay. Yep. All right. So now we want to split this into 2 terms, 2 limits. Let's do that step first. So we're going to have the limit cosine x cosine h minus 1 over h. Now we're subtracting, because we have a subtraction sign, the limit as h approaches 0 sine x sine h over h. Okay, now if we have anything that's only dependent on x and not dependent on h, we can factor it out of the limit, which is based on h. So that cosine x will be pulled out of the first limit, cosine x times the limit as h approaches 0. And then this is cosine h minus 1 over h. Now minus, that sine x can be pulled out, times the limit as h approaches 0 sine h over h. Okay. These are actually the same limits as before. but we'll just put them there. Right, and so remember this limit here, cosine h minus 1 over h, that's equal to 0. And this limit, sine h over h, is equal to 1. And so our expression then just becomes cosine x times 0 minus sine x times 1. And remember, we were solving for the derivative of cosine. And so what this means then is that the derivative of cosine is negative sine. All right, let's do example 10. Let's do the same thing with tangent. All right, so f of x is tangent of x, f of x plus h, tangent of x plus h. That's all we need to go ahead and plug it into our derivative formula. The derivative of tangent of x would be the limit as h approaches 0, f of x plus h, tangent of x plus h minus f of x divided by h. All right. The tangent substitution is not so nice as the sine and the cosine one. But we have this trig identity that the tangent of a plus b is equal to the tangent of a plus the tangent of b divided by 1 minus tangent of a times tangent of b. All right, so this is not the best, but it's what we got to work with. So let's see what happens. We got limit h approaches 0. Now this tangent of x plus h, right, we're going to substitute that in using a equals x, b equals h. We're going to need a little more space, I think. So then what's this going to become? This tangent of x plus h is going to become tangent of x plus tangent of h divided by 1 minus tangent of x times tangent of h. Oops. Yeah, we just need 3. That's that, right? I'm just double checking this formula so I don't mess it up. Looks good. Okay. That is the first term, and then minus tangent of x. And then that is divided by h. Yeah, I don't know if that helps with parentheses there. We can. Okay. Well, in order to combine the numerator together, we're going to have to subtract. And so what we want to do is we want to give these two terms the same denominator. And so this tangent of x, we need to give it a denominator of 1 minus tangent of x times tangent of h. And we do that by multiplying it by that stacked on itself. Because then when we do that, we can go ahead and combine the two terms in that numerator together. And so I'm going to go ahead and write this as the numerator as one big fraction under 1 minus tangent of x times tangent of h. The first part from this first term is just tangent of x plus, I should write my tangents with a curvier t. And then that's going to be minus tangent of x distributed on all that business. So minus tangent of x times 1. And then minus a minus, that's going to become a plus. That's tangent squared times tangent of h. All right, that is our numerator. And then we just divide by h. All right, can some stuff start to simplify? We've got tangent of x minus tangent of x. We also notice we have this tangent of h term now in everything that's remaining. So we can start to pick this thing apart and make it solvable. Let's factor out the tangent of h from that numerator, right? And then that's going to give us a 1 plus tangent squared. All right, that's the numerator of our numerator. Our numerator also has a denominator. 1 minus tangent x times tangent h. All right, so then that would be the numerator, and then we're dividing by h. So I don't know if it's helpful to put parentheses there. You know what? Actually, yeah, speaking of how complicated it is to have multiple numerators and all that business, we could just multiply h times everything in the denominator. That would greatly simplify things, actually. So then this will just be h minus h times that. And it's a lot better to work with. Okay. Now, remember we had said that if anything is independent of h, that we can pull it out. And so that 1 plus tangent squared x is actually independent of h. So that would be 1 plus tangent squared of x in parentheses times the limit as h approaches 0 of tangent of h Actually, let's leave that h factored out. So it'd be h1 minus tangent x times tangent h. Okay. All right. And so the next thing that we're thinking in terms of the big picture right, is that the limit as we approach some value of, let's say if we had some f of x times g of x, we can split that as the limit of f of x times the limit of g of x. And so we want to take this term in the limit and split it in a way that makes it easier for us to find the limit. So let's rewrite what we've got so far. 1 plus tangent squared of x times. Now we're going to write this as the limit as h approaches 0 of, let's get this tangent of h over h by itself. And so then if we factored that out of that term, we would be left with 1 over 1 minus tangent x times tangent h. And so then what that means is we can actually factor those two limit expressions apart. So 1 plus tangent squared of x times the limit as h approaches 0 of tangent of h over h times, close the parentheses, and then times the limit as h approaches 0 now of the other one, 1 over 1 minus tangent x times tangent of h. Okay, so now at this point, we should try to figure out what's going on there. Actually, not worried about that one. Why would I not be? Okay, first of all, let's look at the two limit expressions. The first one, we're dividing by h, and so we can't evaluate that when h equals 0. So we need to figure out a way. That one we can do it graphically. The second one, with the denominator, not going to be as concerned with it going to 0. It looks like we can evaluate at h equals 0, right? Remember that the slope of a line at 0 is equal to 0. Tangent of 0 is 0. And so this denominator will actually just simplify to 1. And we could actually evaluate this limit. Maybe let's just go ahead and do that. And then we'll only have one limit to deal with. So this is 1 plus tangent squared of x times the limit as h approaches 0 of tangent of h over h times. Now this one, if we evaluate it, 1 over 1 minus tangent of x times tangent of 0. Right, and tangent of 0 is equal to 0. And so this just becomes 1. So then really we just need to graph this one. All right. And so we want to know what happens for tan h over h, graphing it with tan x over x. What happens when x approaches 0 on this graph? It looks like then the limit as h approaches 0 of tan h over h would equal to 1. And so our whole expression that we were trying to solve for, 1 plus tangent squared of x times 1 times 1. And so one way to write that then is that we can say the derivative of tangent of x would be equal to 1 plus tangent squared of x. That's not normally the way that it's written, though. And so you might recall, right, that sine squared plus cosine squared is equal to 1. And if we divide each term in here by cosine squared, then we get this other trigonometric relationship that says the tangent squared of x, which is sine over cosine squared, plus 1 cosine squared over cosine squared is equal to secant squared of x. And so it's more commonly written that the derivative of tangent of x is secant squared of x. I guess technically both would be true, but that's the more accepted answer. Okay. Example 11. Let's use this limit method to find the derivative of x times the sine of x. Just like last time, we want to know what's our f of x, what's our f of x plus h. For this one, just substituting in x plus h, we get x plus h times the sine of x plus h. All right, that's all we need to plug it into our derivative formula, right? So this derivative of x times sine of x, that would then equal the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay. Let's see. So we need to figure out what's going on in the numerator. So let's go ahead and expand out that x plus h times sine of x plus h as x sine of x plus h plus h times the sine of x plus h minus x times the sine of x, all divided by h. Okay. Notice now that this one and this one have an x, the other one does not. So we want to group them by if it does or doesn't have an x. And we can go ahead and split the fraction while we do that. And so then that would be x. Now, if we factor out that x, we've got sine of x plus h. And then factor it out of this third term, we get minus sine of x. And then that is going to be divided by h. And then we also have this other term, h times the sine of x plus h over h. All right. Well, that's good. That one cancels. That actually means then we can go ahead and evaluate this limit. So now's a good time to split it into two separate limits. We got the limit as h approaches 0 of x sine of x plus h minus sine of x divided by h plus the limit as h approaches 0 of sine of x plus h. All right, let's see. We can evaluate this one on the end. Um, and then also we have this x multiplied, which is not dependent on h, so we can factor that out. So we have x times the limit as h approaches 0 now of sine of x plus h minus sine of x divided by h plus, now for this one, we just plug in what happens when h equals 0. So sine of x plus 0 is just sine of x. This one, rather than doing any more work here, we're going to recognize that this is the limit definition of the derivative of sine x. Which we already proved is cosine of x. And so we could just straight up substitute that in because we already done the work. Scroll up or rewind. And so then that limit, that whole limit term, then just represents the derivative of sine of x, which is equal to cosine of x. So then what that's saying is the derivative of x times sine x equals x times cosine x plus sine x. All right. So example 12. Use the same limit method to find the derivative of e to the x times cosine of x. All right. Well, we will start by finding f of x plus h. We substitute that in, it's just going to be e to the x plus h times cosine of x plus h. Remember, we discussed earlier, e to the x plus h is equal to e to the x times e to the h. So we can actually rewrite our f of x plus h as e to the x, e to the h times cosine of x plus h. All right, so then now we can define the derivative of e to the x times cosine of x using the limit as h approaches 0 of f of x plus h, so e to the x, e to the h, cosine x plus h, minus f of x, e to the x times cosine x divided by h. All right. We do have an e to the x term in both of those, right? And it's also not dependent on h. And so we're going to end up pulling that one out, right? So first, let's just factor it out here. E to the x, and then we're going to be left with e to the h cosine x plus h minus cosine of x divided by h. All right, so now that we pulled out that e to the x, we can actually pull it out from the entire limit expression. So that'd be e to the x times, now the limit as h approaches 0 of e to the h times cosine of x plus h minus cosine of x over h. All right. We're gonna have to do a little of a weird strategy here. It's called splitting the difference. It's just an algebra strategy so that we can evaluate this limit. But basically, okay, we got the e to the x times the limit as h approaches 0. And now, okay, we got our e to the h times cosine x plus h. We're going to introduce a minus cosine x plus h, which we cannot just pull out of nowhere. So we're going to also introduce a plus cosine x plus h. And then, right, we still also have this minus cosine x from the line above. All right, so we did not change the value, but we just introduced this plus and minus of the same thing. And the reason that we want to do that is because it's gonna affect the way we group this limit expression. So then this one, the next step, we still got e to the power of x times the limit as h approaches 0 of. Now we're gonna group the minus one with the first term. So e to the h times cosine of x plus h minus cosine of x plus h over h. And then now we're going to have plus cosine x plus h minus cosine x over h. All right, now that we've got these two expressions that are added, we can go ahead and split this limit. And also, just like multiplication, distribution, that e to the x, make sure it goes to both. So then we're going to have e to the x times the limit as h goes to 0 of, and we'll write this first term. And we can go ahead and factor out that cosine x plus h as well while we're here. All right, so cosine x plus h, that'd be e to the h minus 1 over h. Okay, that's the first limit. Now we're going to say plus, and then we still have that e to the x that's multiplied. So now the limit as h goes to 0 of cosine x plus h minus cosine x over h. All right. Just like last time, right, we recognize that this is the derivative of cosine of x. Right, the limit as h approaches 0, cosine x plus h minus cosine x over h. That's just the derivative of cosine x, which we already proved is negative sine of x. And so that means then we can just substitute this whole limit expression for negative sine of x. All right, so what do we got? We got e to the x, limit as h approaches 0 of... Also, by the way, if we're looking at this first limit term, we've got these two functions multiplied together. And we can go ahead and split that as two separate limits as well. So that'd be e to the x times the limit of cosine x plus h times the limit as h approaches 0, e to the h minus 1 over h, plus, right, and then we said this is e to the x times negative sine of x, the derivative of that line. This one, right, we took this limit earlier. Graphically. And it equals 1. So then basically we just keep simplifying our expression down. We're almost to the end now. We're going to have e to the x times. Now, can we evaluate this cosine x plus h as h goes to 0? Yes. Right? Cosine of x plus 0. And then times, this one is going to be 1. Plus, actually, let's do minus, right? E to the x times sine of x. And so what this means is that for e to the x cosine x, the derivative that's equal to e to the x cosine x minus e to the x sine x. All right. Example 13. Let's use the same limit method to find the derivative of x squared times ln of x. Now, first of all, we just want to find our f of x plus h. Substituting in x plus h, we get x plus h squared times ln of x plus h. Let's leave it like that for now, and we might have to do some work on that in a little bit. But now we're ready to define the derivative of x squared times ln of x, right? That would be the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay. And so, we see like we have this x squared. So that's going to be the general approach, like kind of some of the other problems we did. We want to basically split the terms if we can factor out an x because x is independent of h. Kind of the same strategies that we've been using on these other problems. So yeah, we're going to want to expand this f of x plus h term. So we've got the limit h approaches 0 of, now what is that going to be? It's going to be x squared plus 2xh plus h squared times ln x plus h minus x squared ln x. Over h. All right. And so then we're going to want to distribute this so that we can separate out the x's from the h's. So that's going to be x squared ln x plus h plus 2xh ln x plus h plus h squared ln x plus h minus x squared ln x over h. Okay. Now we can factor out this x squared that's in these two terms. So we'll have the limit as h approaches 0. We'll factor out x squared from the first and the last term. So x squared ln x plus h minus ln of x. That's the first and the fourth term of the numerator. Let's go ahead and put that one over h. Now, what do we have left? Notice we've got an ln of x plus h in both of those terms, in the second and third term there. So we can factor out that ln of x plus h times, that would be 2xh plus h squared. And that one also, remember, is over h, since we are splitting that. The reason we're splitting that, right, remember, is because we can define this as two separate limits. And also, when we do this one that has the x squared, if it has an x that doesn't depend on h, it can be pulled out to the front. So then that first part of the limit term turns into x squared times the limit as h approaches 0, ln x plus h minus ln x over h. Plus, now then, I guess you want to be careful, since we multiplied x squared times the first one. Remember, that was because it was in the first term. We would not do that on this second term, right? So it would be just plus the limit as h approaches 0 of and then actually we can go ahead and reduce the power of h by 1 in all of these terms since they're multiplied. And so then that would simplify this top part as just the ln of x plus h times, that would be then 2x plus h. Okay. All right, we've seen this one before. All right, we recognize this format now because we've been doing it all day. Recognize that this is the derivative of ln of x, right? Ln of x plus h minus ln of x divided by h. That's the limit definition of the derivative for ln of x, right? We already proved the derivative of ln of x is 1 over x. And the second term, since we got rid of the denominator, there's nothing holding us back from evaluating the limit. So we should be pretty much done here. So we're going to have x squared times, now that whole limit expression, since it's the derivative of ln of x, turns into 1 over x. Then we've got plus. Now, can we evaluate h equals 0 in this second term? Ln of x plus 0, that's ln of x, times 2x plus 0 times 2x. Okay. And so the original function was x squared ln x. All right. That means then the derivative of x squared times ln of x, that's equal to, okay, the x squared divided by x, that just turns into x plus 2x ln of x. All right. And so now let's see if we can deduce the pattern. Similarly to how we discovered a power rule earlier, when we're taking the derivative of a product, how can we break this down into some type of rule that will always work? So first, what we did was we said that the derivative of x sine x, 3 examples ago, was equal to x cosine x plus sine x times 1. Next, 2 examples ago, we said that the derivative of e to the x times cosine x was equal to e to the x times cosine x minus e to the x times sine x. And then in the last example, we said that the derivative of x squared times ln of x is equal to x squared times 1 over x plus 2x times ln of x. So let's see if we can find a pattern here. Well, how about if we're going to multiply two things together, let's just start by giving them a name. Let's say that g is equal to x, and let's say that h is equal to sine x. Okay, now from the power rule, if x has an exponent of 1, then the derivative of just x is 1. And we already proved that the derivative of sine x is cosine x. By the way, this little apostrophe is it's called prime, and it's just a shorthand notation for the derivative. And so they mean the same thing. And so g prime means the derivative of g, h prime means the derivative of h. And so notice then that the derivative of g times h is going to be g times h prime plus h times g prime. All right. And that'll hold up every time, right? So e to the x, if we say g equals e to the x and h equals cosine of x, well, we already proved, right, that the derivative of cosine is negative sine, and the derivative of e to the x is itself e to the x. Then what we get is that the derivative of g times h is going to be, this one, I guess we would call it g prime times h plus g times h prime. Right, and I underlined that it's not supposed to be equals, but trying to emphasize that negative sine x is our h prime. And then lastly, right, with the x squared ln of x, we could say g equals x squared and h equals ln of x. Well, from the power rule, right, g prime would just be 2x to the power of 1. For ln of x, remember we proved that was 1 over x. And so now this one is g h prime plus g prime times h. All right. And so then that is how we discover the power rule, right? And so to formally define it, the derivative of g times h would be g times h prime plus g prime times h, or any other way you want to multiply that around in whatever order. But that's, oh wait, not power rule, whoops, product rule, sorry about that. That is how we discover the product rule. Okay, example 15. Let's do the same limit method to find the derivative of x over 2x plus 1. All right, first of all, we got our f of x. What's our f of x plus h? Plug in x plus h, we get x plus h over 2 times x plus h plus 1. And we can also write that as x plus h over 2x plus 2h plus 1. All right, now we're ready to define the derivative. So the derivative of x over 2x plus 1, that would be equal to the limit as h approaches 0 of, we're going to need more space. That's going to be f of x plus h minus f of x over h. And before we move forward, we see we're going to want to mess with that numerator. So we're going to need to give it a common denominator, and we'll just do that by multiplying by the other denominator stacked over itself. So 2x plus 1 over 2x plus 1 on the left side, and 2x plus 2h plus 1 over 2x plus 2h plus 1 on the right side. All right, and then when we do that, it's just gonna combine the numerator into a single term, right? And then we can also, we could even also go ahead and multiply this by h as well, since it's the denominator or numerator. When we divide it by h, it's going to get multiplied in there. So then that means that we have here x plus h times 2x plus 1 minus x times 2x plus 2h plus 1 over h times 2x plus 2h plus 1 times 2x plus 1. All right. And so then, like before, we want to separate it out based on if it has an x or not. And we'll probably, that's the general strategy we've been using, right, is separate out if there's a limit that maybe depends on x versus one that depends on not x. And so we want to expand all this stuff out so that we can then kind of recategorize it or regroup it. So we're going to take the limit as h approaches 0 of, and so then that's going to be 2x squared. I'm going to do the FOIL on the first term, plus 2xh plus 1 times x plus 1 times h minus, and I'm going to go ahead and put that minus x times each term so that we just don't have any parentheses anymore. So that'd be minus 2x squared minus 2xh minus 1. Oh wait, minus x. Minus 1 times x. All right, and then that is going to go over, we got h. I'm going to leave the h out of it first and just figure out this term. I'm going to do 2x times each term and then 1 times each term. So it'd be 2x times 2x, 2x times 2h, 2x times 1, and then 1 times 2x, 1 times 2h, and 1 times 1. Okay. Now let's see if some stuff might cancel away. 2x squared minus 2x squared, 2xh minus 2xh, x minus x. That worked out. Now we're going to take the limit as h goes to 0 of the only thing left in the numerator is h. And didn't we also have 1 multiplied times everything in the denominator? So then our numerator will just become 1 and that h will actually go away. And so then what's left, we got to combine any like terms if we see them, right? So we got 4x squared plus 4xh plus 2x plus 2x, that's 4x plus 2h plus 1. Okay. Well, now that we got that h out of the denominator, then we're going to be good to go for evaluating this limit, right? And so it's going to be 1 over. And then we're just going to evaluate everything as if h equals 0. So 4x squared, if it has an h, it goes away. So plus 4x plus 1. All right. And so the original function that we had, remember, was x over 2x plus 1. And so then what we're saying is that the derivative of this is going to equal 1 over 4x squared plus 4x plus 1. And, you know, just as like a side note, we'll come back to this in a little bit. This expression would just be mathematically equal to 2x plus 1 times 1 minus x times 2 divided by 2x plus 1 squared. We'll come back to that in a second. If you remember how we kind of deduced the pattern for the power rule, just seeing it in that format is going to help us to deduce a pattern for when we're dividing later on. Let's do a couple more examples, and so we'll have enough evidence to find the pattern. So example 15, we're going to do the same limit approach to define the derivative of e to the x over x squared minus 3x. All right, so that's our f of x. What is our f of x plus h? That's going to be e to the x plus h over x plus h squared minus 3x plus h. Okay, so we definitely want to kind of do some stuff to expand this out, simplify it out a little bit. Remember, e to the x times e to the h, that's e to the x plus e to the h. X plus h squared, we've seen this one a couple times. That's x squared plus 2xh plus h squared. And then this one, minus 3x minus 3h. All right. I think that's about as good as we're going to get it. So then we can define the derivative of e to the x over x squared minus 3x is the limit when h goes to 0. Let's move this down a little bit. We're going to need some space here. The limit as h goes to 0 of f of x plus h minus f of x divided by h. All right. And so similar to before, right, we're just going to need to expand this out. We're going to need to combine the numerator. So we'll do that by giving these two expressions the same denominator. All right, x squared minus 3x over x squared minus 3x. On this side, over here, it's going to be a long one. X squared plus 2xh plus h squared minus 3x minus 3h over that same thing. So now to move forward, we do want to do the expansion within the numerator, but then with the denominator, it might be more convenient to just leave it separated for now. And since we've got this e to the x times both terms, we could even go ahead and factor that out of the entire limit expression. And so now we can say this is equal to e to the x times the limit as h approaches 0. And now we factored out the e to the x, and now we can distribute what we have left. So we've got x squared times e to the h minus 3x times e to the h minus, now remember that minus e to the x is going to have to go all of these places. And so each one of those terms, the sign is going to flip. We got x squared e to the x. Wait, no, there's no e to the x. What? Just -1. All right, so that's going to be minus x squared minus 2xh minus h squared plus 3x plus 3h. That's the numerator. Now for the denominator, we can go ahead and combine that h with our denominator, and let's just leave it simply as h. Well, I say simply, relatively simply. X squared plus 2xh plus h squared minus 3x minus 3h times x squared minus 3x. All right, and one thing I notice now that I'm looking at it is that we got this x squared minus 3x. We've got an e to the h times x squared minus 3x. And then we've got like a minus x squared plus 3x, which is like a negative x squared minus 3x. So it looks like we might be able to factor that out of each of these terms. And so then the next step, we've got e to the x times the limit as h approaches 0 of. So then, yeah, we'll leave this e to the x factored out. E to the h, is now I got x squared minus 3x. Now, we want to group that x squared plus 3x over here, right? So minus x squared plus 3x. And then we'll go ahead and write all the other terms. So minus 2xh minus h squared plus 3h. All of that now would be under this big denominator. H x squared plus 2xh plus h squared minus 3x minus 3h times x squared minus 3x. Okay. Now, then this one, right, we're just going to call negative x squared plus 3x equal to negative 1 x squared minus 3x. So now we've got e to the x times the limit, h going to 0. Now, notice if we do that, we can write this in terms of x squared minus 3x. That means we can factor it out of this as well. So we got x squared minus 3x times e to the h. That'd just be minus 1. Okay, and then now that stuff is still there on the side. Minus 2xh minus h squared plus 3h. All right. Yeah, so with this, at this point, it might be a good idea to break it up. So we'll write this denominator under both of them. And now this x squared minus 3x term is going to cancel out there. And these two terms, we're going to want to write them as two separate limit expressions. And so first of all, we're going to have e to the x times the limit as h goes to 0. If you remember from earlier, this e to the h minus 1 over h, we already solved it. And so let's clump that together. That would then be multiplied by 1 over, and then all the rest. X squared plus 2xh, h squared minus 3x minus 3h. All right, and then that would give us just 1 there. Okay, and then for the other part, right, remember that e to the x is going to go on both because it's multiplied out in the very front. So then we're going to have e to the x times the limit as h approaches 0. Now using this second term, okay, I didn't notice this earlier, but we can actually go ahead and get rid of this h. Every term in there has an h. And that's going to help us to simplify this next line. And now it looks like we should be able to even evaluate it. Since we removed the h from the denominator, we no longer have the issue of dividing by 0. And so then for this one, we get negative 2x minus h plus 3 over x squared 2xh plus h squared minus 3x minus 3h times x squared minus 3x. Okay. And so then this first part, now that we've got these two terms multiplied by each other, we can write them as two separate expressions. So we have e to the x times the limit as h goes to 0 of e to the h minus 1 over h times the limit as h goes to 0 of this. All right, and then we're going to have this other part. We're going to have e to the x multiplied. We can go ahead and evaluate this limit, right, when h equals 0. That would just give us, now I got negative 2x plus 3 over now notice when this goes to 0, that goes away, that goes away, that goes away, and they're actually equal, right? So this would be x squared minus 3x times x squared minus 3x, or x squared minus 3x squared. All right, and so remember we did this limit, we solved it graphically earlier, it equals 1. So we got e to the x times 1. Now we can also evaluate this one when h goes to 0. We got x squared, that goes to 0. We just have x squared minus 3x. And so then finally, the original function was e to the x over x squared minus 3x. So then we can say that the derivative of e to the x over x squared minus 3x, that would be equal to e to the x over x squared minus 3x plus e to the x times negative 2x plus 3 over x squared minus 3x squared. And just also, right, this would be equivalent to x squared minus 3x times e to the x minus e to the x times 2x minus 3 divided by x squared minus 3x squared. And we'll get to that when we deduce the pattern. That's just the more convenient way to see the pattern, but it's equivalent to the same answer. Okay. Example 16. Use the limit method. Find the derivative for our f of x equals ln of x over sine of x. If that's our f of x, then our f of x plus h would just be ln of x plus h over sine of x plus h. All right, that means then that the derivative of ln of x over sine of x can be defined as the limit as h approaches 0 of, now we need to do f of x plus h minus f of x over h. right. The first thing that we are going to want to do is to give this a common denominator so that we can combine these two fractions. So we got sine of x plus h, sine of x. The only way to combine them is by multiplying by the other denominator. So the left one will do sine of x over sine of x. And the one on the right will be sine of x plus h over sine of x plus h. Now, they'll have the same denominator. We can combine those. All right, and we can also combine that h with the denominator. So then we got the limit as h approaches 0 of ln x plus h times sine of x minus ln of x times sine x plus h over, now we can have h multiplied by all of that, sine x plus h times sine of x. All right, and so we introduced that strategy earlier where we have, sometimes we have a complicated fraction, we can kind of do like a plus minus to make it where we can evaluate it. We're going to do that strategy here, splitting the difference. So the first things first is let's just write it how we have it. So just the numerator ln x plus h times sine of x minus ln of x times sine x plus h. Now what we're going to want to do is we're going to add ln of x times sine of x. And then since we added that, we're going to also subtract ln of x times sine of x. All right, then that's our numerator. Still over h sine x plus h sine x. Okay, now why would we want to do that? That's because now we can kind of lump it and group it strategically. So what we want to do is we want to take advantage. If you remember how on a similar previous problem, let me see, we get to a point where we recognize that, okay, we've got the derivative of something written as a limit expression. And so basically, we're kind of planning ahead on this example to try to reach that with the ln of x. And also, as it turns out, when we introduce this, it creates a way that we can factor out sine of x to then get an ln of x plus h minus ln of x. Right, and so this is the first and the third term coming together. Factoring out the sine of x, and then, oh wait, first and the fourth term, I mean. All right, and so then, likewise, we're going to group these. And we can factor out ln of x from that. So then we have minus ln of x. If we factor out a minus ln of x from both of these, then we've got sine x plus h minus sine x. And look, now that one also, we can see where this is headed, right? We can see that we're about to substitute that with its derivative definition. So let's make sure we just accounted for everything. First and fourth term combined to make that one. Second and third combine. Okay, cool. Now we just need our denominator. And you know what? Let's go ahead and separate these, right? So this one will be h sine x plus h sine x. This one will have the same denominator since we're splitting it from the same fraction. All right. Awesome. Now it's coming along, right? We have these two limit terms that are separated by a minus sign in there. So that means we can write two separate limit expressions. We also have sine x multiplied by 1. We've got this ln of x multiplied by the other. We can just do all of that at once. So this one on the left, we're going to pull out the sine of x times, now the limit as h approaches 0 of ln x plus h minus ln x over h times sine x plus h times sine x. That's one. We're going to close the limit parentheses. Now we're going to make a separate limit expression. Now we're going to factor out that negative and the ln multiplied by the limit expression. So it would be minus ln of x times the limit as h approaches 0 of, and then we don't write the ln part anymore, sine x plus h minus sine x over h sine x plus h times sine of x. All right. So now we can kind of see how we've got the makings of the limit definition, but it's still jumbled together. And so remember, we also have that property of limits where we can separate two limits multiplied together. So we can rewrite this then as the limit, or sine of x times the limit as h going to 0 of, now we're going to lump the ln derivative part and we're going to write that as a separate expression times the limit as h goes to 0 of. Now what would we, if we divided out this, what would be left? It'd be 1 over sine x plus h times sine of x. All right, and that one is fine, right? Because we don't have the h in there, we can find that limit. And so then that's what happens to the left part. Very similar thing is about to happen on the right side. So we've got minus ln of x times the limit as h goes to 0. We're going to split this whole thing into two terms multiplied by themselves, right? So sine of x plus h minus sine of x over h. And then also now times the limit as h goes to 0 of, what's left? 1 over sine x plus h times sine of x. And like the other one, since there's no problem with putting in h equals 0 in that last part. Okay. So then there we go. We're mostly done. Right, this part, we said that the derivative of ln of x is equal to 1 over x. And this part, the derivative of sine of x is cosine of x. So then our expression that we're solving for, we've got sine of x times 1 over x times, we can evaluate if h equals 0. That's going to be 1 over sine of x plus 0 times sine of x. That's sine of x squared. But also, it looks like it'll cancel. All right, that's the whole thing. Okay, now minus ln of x times, that part is cosine of x, times, this is actually the same as the other side. We got 1 over sine of x plus 0 times sine. Well, actually, in order to show the pattern that we want to see to determine our rule for dividing derivatives, rather than canceling it, we're going to go ahead and combine, since these will have the same numerators. So what we can do is we can say 1 of x in our numerator times sine of x over sine squared of x minus ln of x times cosine of x over sine squared of x. And so then basically what we've been trying to solve for, the derivative of ln of x over sine of x, that would be then 1 over x times sine of x minus ln of x times cosine of x over sine squared of x. Okay. So now, just like people had to back before we had the certain rules defined, can we deduce a pattern? For quotient derivatives. Quotient just meaning divide. If you remember 3 examples back, we said that the derivative of x divided by 2x plus 1 is equal to 2x plus 1 times 1 minus 2 times x divided by 2x plus 1 squared. All right. 2 examples back, we said that e to the power of x is equal to x squared minus, or over x squared minus 3x. The derivative of that, oh, I should have done that color too. Oops. And then 2 examples back, we said that the derivative of e to the x divided by x squared minus 3x, that's going to equal e to the x times x squared minus 3x minus e to the x times 2x minus 3 divided by x squared minus 3x squared. And then in this last example, we said that the derivative of ln of x over sine of x was equal to 1 over x times sine of x minus ln of x times cosine of x divided by sine squared of x. So what pattern do we see? Well, just like last time with the product rule, and you'll see I already separated them into colors, we can define like a G and an H in each of these. So let's let G be X in this example. Then what would G prime be? Would just be 1 from the power rule that we did first. All right, and then if we said H is equal to 2x plus 1, well then H prime, if we use the power rule, is just 2. Okay, looking at the next example, let's call G equal to e to the x, and so G prime, the derivative of e to the x, is itself e to the x. For the other one, if we're dividing by x squared minus 3x, let's call that h. And then h prime, we can also find that using the power rule as 2x minus 3. And then lastly, we got ln of x over sine of x. So let's call G equal to ln of x. We've done the derivative earlier, is 1 over x. H, the thing we're dividing by, is sine. And we did the derivative earlier, is positive cosine. And so now we should be able to see the pattern that we call the quotient rule. And what this says is when we are taking the derivative of G over H, it is going to be H times G prime minus G times H prime over H squared. And that one is a little, maybe it's not so easy to remember. And so another way that might be better is if instead of calling it H, we call them low and high, as in, high and low. And you can pretend, you're a 6-year-old skipping down the sidewalk, and you got low-de high, high-de low. Over low squared. And that's just a little easier to remember. All right, next, we got example number 17. Let's use the limit derivative method to find the derivative of f of x equals e to the power of cosine x. Okay, well, like before, we need to find our f of x, we need to find our f of x plus h. F of x plus h, just plugging in x plus h, we get e to the power of cosine of x plus h. I should also, before I jump into the problem, I'm supposed to provide a hint with this one. So this hint would be like given with the problem. Just as a hint then, okay, cosine of x plus h is going to be basically equal to cosine of x minus h times sine of x. And e to the power of some u will be basically equal to 1 plus u, only for very, very small values of h or u. All right, so that one, I guess we'll see where it comes in later, but that type of hint would have to be given with the problem in order to solve this one. All right, so then let's get into it. We got our f of x, we got our f of x plus h, so we're ready to define the derivative. The derivative then of e to the power of cosine x, it, like all the other times, is going to be the limit as h approaches 0 of f of x plus h, so e to the cosine of x plus h, minus f of x, e to the cosine of x, divided by h. In order to move forward, we want to factor out that e to the cosine x, but it's maybe not exactly possible from both sides. But what we can do is we can say e to the power of cosine x plus h. Now I want to introduce an e to the power of cosine of x. And since I did that, I have to also enter e to the power of negative cosine x. That way, those would multiply and cancel themselves out, so I don't change the value. All right, now what would be the reason of doing that is that we want to factor these things out. So then we're going to have the limit as h goes to 0. Now e to the power of cosine x, we're going to factor that out. And also remember, when we have two exponents, same base multiplied, we can combine their exponents. So we're going to combine these exponents together. So we'll have e to the cosine x times e to the cosine x plus h minus cosine x. And all of that is the exponent of this number. Then minus, we factored that out, so it's just minus 1 divided by h. Right? And that e to the cosine x does not need to stay in the limit. Since we factored it out of everything, we can now actually bring it all the way out. And that's now multiplied by the limit of h going to 0. E to the cosine x plus h minus cosine x minus 1 over h. Okay. Now, remember we had these hints about when we have very small values of h or 0. So now, for example, we have this cosine x plus h. We had this hint for cosine x plus h. So our hint is that cosine of x plus h is basically equal to cosine of x minus h times sine of x for very small h, such as when the limit of h approaches 0, right? So the only reason that we can do this is because we're taking the limit to 0. And even then it's, but yeah, anyways. So then let's see. So now what happens? Well, now we still got our e to the cosine x out front. Still got limit h approaching 0. Now instead of e to the power of cosine x plus h, we can call this e to the power of cosine x minus h times sine x, and then we also had that minus cosine x. And then that's minus 1, and it's all over h. Now notice in the exponent, we've got plus cosine and minus cosine. So that will cancel. So then that leaves us e to the power of cosine x times the limit as h goes to 0 of e to the negative h times sine x minus 1 over h. And so then we had this other hint that e to the power of u is basically the same as 1 plus u for very small u. And so in order to make sense of this kind of more crazy exponent, we can just define u as negative h times the sine of x. And so then e to the negative h times the sine of x, that's like our e to the u expression. That's like saying 1 plus negative h times the sine of x. And so we can substitute that in for this. So then now we've got e to the power of cosine x times the limit as h goes to 0. Now, instead of e to that exponent, we're just going to write this as 1 minus h sine x. And then we've also got minus 1 over h. All right, 1 minus 1. And then also when we do that, now I've got negative h sine x over h. So then the h's will also cancel away. All right. So then what does that give us? E to the power of cosine x times the limit as h goes to 0 of negative sine x over 1. Okay. So then that means that the derivative of e to the power of cosine x is just equal to negative sine of x times e to the power of cosine x. All right. This will be our last example. We're going to use the limit method to find the derivative of ln 5x squared plus 2x. And just like the last one, we would need to be given a hint in order to solve this problem. And that one is that ln of 1 plus u is going to basically equal u for very small values of u, such as, the limit to 0. So we got our f of x. Now we need our f of x plus h. All right, so it's going to be the ln of 5x plus h squared plus 2x plus h. Okay, we are going to clean this up as much as we can before we start doing the limit. So that would be 5 times, remember x plus h squared is x squared plus 2xh plus h squared. And then plus 2xh would be plus 2x plus 2h. All right, so then we're still cleaning up our f of x plus h. It's ln of 5x squared plus 10xh plus 5h squared plus 2x plus 2h. Do we have any? Nope, no like terms. All right, that's good enough. All right, now we're ready to move on and define the derivative. So then the derivative of ln 5x squared plus 2x, that's going to equal the limit as h goes to 0 of f of x plus h ln of this long expression minus f of x. And then divided by h. All right. We talked about this earlier, right? Remember, if we have an ln of a minus an ln of b, we can combine that under the same log as ln of a divided by b. So then this turns into the limit as h approaches 0 of ln 5x squared plus 10xh plus 5h squared plus 2x plus 2h divided by 5x squared plus 2x. And that is divided over h. Okay. Now, just like last time or the other times, when we have a kind of a complicated fraction like this, especially within the limit term, then we can actually go ahead and pull it out. Also, that ln, if you wanted to, we could say that this is equal to ln of the limit as h goes to 0. And you could do that, but actually in this case we don't want to do that. That's because we were given this hint, and so we're going to basically try to restructure what we've got to match the format of that hint so that that's usable for us. But yeah, in another problem we might try that, but this problem is actually going to be better to leave it like this. But what we should be doing is we should take this big fraction expression and we want to split it in terms of if it does or does not have an x in it. So we got the limit as h approaches 0 of the ln and then what do we have in there? What has only an x, right? Not just that it has x at all, only has x. We would have 5x squared plus 2x. And then the other terms, we've got 10xh if it has an h. So actually, I guess we're splitting it if it has an h or doesn't, not if it has an x or doesn't. Because if it's independent of h, we can work with it, pull it out of the limit and stuff. Okay, so that's how that one simplifies. Right, this one is just 1. So now we're taking the limit as h goes to 0 of the ln of 1 plus ten xh plus 5h squared plus 2h over 5x squared plus 2x. All right, that's inside the ln. The ln is our numerator. Our denominator is the h. Okay. This is where we want to pull in our hint that the ln of 1 plus u is basically equal to u for very small u, such as the limit approaching 0. And so then what that means is that if we define u equal to 10xh plus 5h squared plus 2h over 5x squared plus 2x, right? Notice as h approaches 0, everything in this denominator is going to turn to 0. So that means we do satisfy the condition that it's a very small u. And so then ln of 1 plus this I'm supposed to be faster. Ln of 1 plus u come on. It's going to basically just equal what we have for our u expression. And so then that just means that we're going to clean this up a little bit. Instead of writing ln of 1 plus that stuff, then we'll just have 1 plus that, or just that stuff. So yeah, 10xh plus 5h squared plus 2h over 5x squared plus 2x. And that's still over our denominator of h. All right. Now, since we have an h here, h, it'll all cancel away. And so then we're left with the limit as h is approaching 0 of 10x plus 5h plus 2 over 5x squared plus 2x. All right, and we can evaluate h equals 0 now. There's only one term that still has a h, so that one will just go to 0. So this one will give us 10x plus 2 over 5x squared plus 2x. And so, in other words, we started with the derivative of ln 5x squared plus 2x. And we get that it is 10x plus 2 over 5x squared plus 2x. All right, and so now let's see if we can deduce the pattern for nested or chained type of functions. All right, so the first example that we did for this type, we had said that e to the power of cosine x has a derivative of e to the cosine x times negative sine of x. And the other one that we just did says that if we have the derivative of ln of 5x squared plus 2x well, then that would give us 1 over 5x squared plus 2x times 10x plus 2. And so if we look at this first one, let's say that we've got like g would be, I guess, e to the x, and h would be cosine of x. So then basically this is representing g of h of x, right? We're plugging in the value of h into our function of g. So that's why it's called like a nested or a chained. And so then just to help us see the pattern, right, what would be the derivative of e to the x? It would be itself e to the x. And the derivative of cosine would be negative sine. All right. Now, similarly with the ln example, our g function, what's the main function, would be ln of x. And then we've plugged in h, 5x squared plus 2x, as the value of x in g. So it's g of h of x, right? So then g prime would be 1 over x. H prime, by the power rule, would be 10x plus 2. And so now we can see the pattern for what we call the chain rule. So the derivative of g of h of x equals g prime of h times h prime. All right. So that's my video for the limit definition of derivative. I hope you got a lot of good practice evaluating these complicated derivative expressions. Also, it's a nice introduction to the idea of derivatives, as well as teaching you the chain rules and power rules and all the rules that we derived ourselves, just as if we found ourselves in the 1800s, knowing only what they knew then. Um, we just determined all the rules for ourselves. So please like it, subscribe, share this channel if you found it helpful. See you next time.